Hello, so we are now going to discuss the skin effects. Here are the four Maxwell's equations which we used to write always in the beginning. As this effect happens for the conductors, so therefore we will be taking a non-zero J, which is the current density, and that is according to Ohm's law equal to sigma times E. We will still assume that there are no free charges inside the conductor, and which is true in fact in general. Okay, so now we will take the curl of equation number 1.2, which is the curl of E equation. So the curl equation of E, once taken the curl, would be written as this. So now we will put the values of del cross B and we will solve this using the identities of the calculus. So this is going to be del to E minus del of divergence of E plus 1 over C, and del cross B is mu H. So we will have mu upon C del over del T, and we will have 4 pi by C and the J, and plus 1 over C del over del T. Or from here onwards, we could write del to E. This is going to be 0. This we will ignore because this is going to be the second order term in T. So therefore this is going to be very small as the time is larger compared to the lead. So therefore this is going to be the leading term. So we will have del to E minus mu by C 4 pi mu by C square J, which is essentially del J by del T, and that's equal to 0. Now we will multiply this equation by the sigma and try to write E as J. So multiplying 2 by sigma and using J sigma E, what we will get? We will get del to J minus 4 pi sigma mu upon C square del J by del T, that's equal to 0. Now so this is obviously a diffusion equation. However, this would have been a sort of wave equation hadn't this term been there. So the solution will of course be in the form of wave. So let the solution be J is equal to J0 e to the power I omega t and minus in fact I kx minus omega t k dot r minus omega t. So if we do that and try to write this in terms of J0, what we will get is the following. We will get del to J0. I'm not operating the J0 term. In fact, let's first write this as the J0 K. Let's write the R dependent over here. So this is the function of R and T. So let this be written as, in fact, let me write this as J is equal to J0 R e to the power I omega t. So therefore we will have del to J0 minus 4 pi sigma upon C square e to the power, in fact this should be minus I omega t because we write e to the power I k dot r minus omega t. So this minus del j by del t will give minus I omega. So therefore we are going to get I 4 pi sigma omega by C square times J0. Now could replace this by something more interesting, which looks like tau square J naught. So this is my equation number 3. We had defined tau square to be I 4 pi sigma mu omega by c square, or tau is going to be square root of this whole quantity. So this is going to give you I square root I, and then I will take 2 outside. So this is going to be root I upon c we will get, and then root 2 I upon, in fact, root 2, and then the rest of the thing is going to be c upon 2 pi sigma mu omega, and I will write this as delta, with delta being defined as the c by 2 pi sigma mu omega square. So this delta is called the skin depth, and I will interpret this little bit later. However, let's check what is happening over here. So this could be written as square root of I, that's going to be 1 over I upon root 2, and then square root 2, they will cancel. So we will have 1 over delta. So the tau is 1 over delta, and we have 1 plus I. So what does it mean? This means the K, and so both K, the real part of K and the imaginary part of K is going to give the skin depth. Now this clearly says that the wave is attenuated. How? Let me just try to write this J in the full form. So J would have been written as J is 0 e to the power I k dot r minus omega t. However, this K would have been an complex K, so therefore I will represent it by the K tilde. So this K tilde would have been a combination of the original K plus essentially the beta. So these are the vectors, and then of course we could dot these things with the r minus omega t. So with this, what we could recover is the original ik dot r minus omega t, and other than this, what we had recovered is essentially I square, which is minus I beta dot r. So this is my usual J, the actual wave. So essentially we could write, if we wish to, J tilde, that's equal to J original times e to the power minus beta r, or we could also write this as J0 e to the power minus r upon beta. So let's fix actually this to be some direction. So this is x direction. So what we could write this as the beta and x, or we could write this as e to the power x upon, what is beta? Beta is given by 1 over delta, so this is going to be x over delta. So therefore, from here we conclude that j is going to be, j of x is going to be equal to mod of these things is going to be e to the power minus x by delta, and that means after traveling a distance delta, the wave would attenuated by a factor of 1 over e, and that's why we say that beta, or the inverse of delta, also represents the e folding. So this means the wave gets attenuated by 1 over e in traveling a distance equal to skin depth, and this means inverse of 1 over delta, which is beta, will represent number of E foldings. That means how many times we have got these factors of E. So this is what is happening. See, we had the J, which is oscillatory, or you could in fact say that this is J0. In fact, I would have written this as J, and this is the J original, and then this e to the power minus I beta. So essentially the effect has been over here itself. J0 of x is J0 e to the power minus x upon delta. That's what we could write. So this is J0. So J0 gets folded by a factor of E. So that's like this in every interval of delta. So this is how it will keep falling for one interval. Or if we want to give the whole picture, so this is how it should sharply fall. The whole picture of J in terms of x should be somehow something like this. So it should slowly diminish. Okay, so this completes the idea about the skin effect. We had already seen in our previous lecture that for this reason, we hardly have any electric wave inside the conductor. Only the magnetic wave could propagate. Okay, so thanks a lot.